All right, there. Started recording. Forgot to start the recording, but we will start it now. All right. So since I just started recording and you guys are writing this, I'm going to do a quick boy explanation. Basically, gear train, speed ratio. Those mean the same thing as gear ratio, which most people have heard before. When you're writing it math, that is lowercase e. There are different ways to define it. Basically, these ways. This first one is about the tooth count. So how many teeth are in the gear? It's the number of teeth driving, so being driven by a motor, the gear, which is on the motor, divided by the number of teeth of the driven gear, which is whichever one is connected to that gear. That is the same thing as this next one, which is the speed out divided by the speed in. So how quickly are the gears rotating? And then that is equal to the torque in divided by the torque out, which we have covered torque in previous classes, which it is force times distance. And in this one, that is actually multiplied by the efficiency, which is this weird in over here, which usually you can exaggerate to make it make sure you don't confuse it. And then down here, we just have that whole thing. Basically, gear ratio is equal to number of teeth drivers divided by number of teeth driven, which is equal to speed out over speed in, which is equal to torque in over torque out times efficiency. And in terms of efficiency, that's the efficiency of the system, which can be affected by friction, warping, binding, and some other things, which basically just means any imperfections in your system. And for now, we're just going to say that efficiency is 0.95, which is 95% efficient, which is hopeful. All right. How are you guys doing on writing stuff down?
I finished writing, but I also have a question.
Yep.
Why is it that math uses so many Greek letters rather than just different symbols? Because
so
N you showed is actually a Greek letter.
Yeah, it is. It is. I just didn't. Most people don't know Greek letters, so I just called it a weird N, but you're right. The reason why is because when you go through the alphabet, so when you're doing math, right, if you're doing algebra, let's say I have x plus y equals z, right? That could work, but we might be using those for coordinates, right? So maybe we want to do, I don't know, a plus b equals c, right? Well, what if we have this equation, right? And then we want to, let's say this is linear, right? So this is in a linear format. What if we want to take that linear thing but make it angular, right? So let's say this is actually a good example is acceleration and velocity. So acceleration is denoted by a, right? And that makes sense, a for acceleration. But what about angular acceleration? It's still acceleration, right? But now it's angular, and we need a way to differentiate that. We can't just say it's a, because if we do that, these two are the same, and now we're going to get all confused, right? So an easy way to differentiate them but keep them similar is by using the Greek version. So alpha is basically the Greek equivalent of a, right? So these two are similar but not the same because one is angular. And in math, we use a lot of Greek letters, one, because we run out of symbols, and two, because it allows us to equate things and relate them more easily. Another example of that is v is velocity, and angular velocity is omega. Words. Similar, but different. So that sort of thing happens a lot, and really the reason why is because we want to keep in mind that two things are very similar and related to each other, but they aren't 100% the same. That's oftentimes why Greek letters are used. There are other reasons, and there are differences between math and engineering math in that. For example, in standard math, like if say you're a math major, right? You end up basically there are sometimes equations where you use most symbols. It is also helpful for certain symbols to mean certain things, right? So in engineering, we have rho, which looks like a P, but it's actually a rho, and that equals density, right? That is always basically true. And if we assign rho to equal density, then we should not ever assign rho to equal something else. Like we wouldn't assign rho to equal volume or something, right? And if we assign letters or symbols to equal something specific, that kind of like, it takes that letter or symbol, and therefore it's kind of out of our deck of choices when we want to assign something else. So, you could pick a letter or a symbol or a Greek letter, and it's probably got something assigned to it. Capital V is volume, lowercase v is velocity. I don't know. Throw out a letter, and I can probably find something that it is assigned to. So really, the simple answer to your question is there just aren't enough letters. And why Greek letters instead of just random symbols is so that you can relate things. Does that make sense?
Yes, thanks.
Okay. All right. So we will clear all, and we will go to the next slide. So some of these I'm going to skip through. This one's kind of important, but I'm not going to go over it too hard. Basically, gears have their whole own science to them, honestly. So if I looked at a gear real close up, and this might be a bad drawing of a gear, but we'll see if I can do it. Kind of. All right. If I looked at a gear real close up, right, it would kind of look like this. Gears have different measurements in them, and there's only one that matters for us, and that's the pitch diameter, okay? Basically, there's an outer diameter, which is at the edge of the teeth. There's the inner diameter, which is at the base of the teeth. And then there's the pitch diameter, which is between the two, okay? So the pitch diameter here is what matters for what we're doing, which is basically gearing. And the reason why it matters for what we're doing is because that's within the mesh space. So if we have a gear here and another gear that's meshing with it, right, it'll look something like this. And if we drew a circle through the pitch diameter of this gear and a circle through the pitch diameter of this gear, their pitch diameters would only meet at one point, right? So the pitch diameter is kind of the easy way of simplifying gears down into circles when you're doing gear ratios. Because if I were to say, same thing, but if I were to have two meshing gears, right, and I were to draw their outer diameters instead of their pitch diameters, like so, they would meet at 2 points, right? And those circles would be intersecting, which would cause binding and not work. So we always look at the pitch diameter. You probably won't come across something where that's super important, but you might end up seeing something that says like the pitch diameter of this gear is this much. and the pitch diameter of this gear is this much. And the diameter of a gear that you're looking for is the pitch diameter. So it's just something nice to keep in mind. You don't want the tooth diameter. You don't want the inner diameter, only the pitch diameter. If you're looking at making gears, then you'll want the pitch, or then you'll want to know about other stuff like tooth depth and spacings and stuff like that. But for this initial class, we're not going to be looking at that because that gets into some crazy wacko math that you guys are not going to need to know right now.
I mean, I've been making gears.
Yeah. Well,
It's been a lot. Like, it's crazy.
if you have CAD, that makes it significantly easier because it does most of the math for you.
Yeah.
Which is very nice because
I
gear
took a
math, I'm
tooth,
not a fan of.
like a certain tooth, I estimated on how to make one, and then I extended that tooth in CAD, and then I had to find out where the hole was, like where I'd put the axle, and then the spacing between the gears, like I had to get it exact.
Yeah, there's math so that you can figure out exactly how many teeth and spacings and all that jazz. There is also on most CAD softwares like a gear function where you can basically take a circle of some pitch diameter and turn it just into a gear. It'll do it
Yeah, I
for you.
haven't found out how to do that, so I've had to make them all myself.
All right, so let's see. Do I want to do this one yet? No, not yet. We're going to try to look at some examples / problems. I think what we're going to do, yeah. All right, so let's look for now at this one. So there are some important pieces of information here, and I'm going to ask you questions based on them. So we have a bunch of gears, right? We got a 16 tooth gear, we got a 56 tooth gear, got a 15 tooth gear, got a 16 tooth gear, got some diameter, and a wheel. And I guess it doesn't have a number of teeth for this guy, but I'm not going to worry about that. We're just going to worry about the output of this. So basically what this is saying is you've got two motors here that are both driving one gear, and that gear then has an output shaft, right? Does that make sense? Yes, no, maybe so?
Yes.
Cool. So this will be real simple, but I want to basically say what is the gear ratio for this little system here? And that's our output. And so let's just make a ratio first. We're going to use the first one, which is E, which is our gear ratio, equals our in drivers divided by our in driven. Okay. And remember, big N means number of teeth. So basically, which ones are drivers? This is where you guys start answering stuff.
I can't. Hold on, let me figure this.
Guessing is welcome.
Is it the one, or is it the two that are 16 torque?
Yes. So the drivers are the ones that are connected to the motors in this case. So these two over here. If we were looking down the system, so further down the system, let's say we were looking at this sprocket and chain setup over here. Which one of these two here, which one of these two sprockets would be the driver? We'll say the sprocket right here, this is number 1, and the sprocket over here is number 2. Which one is the driver?
1.
Yep. Whichever one basically is the closest to the motors in the whole system is the driver, and the one that is closest to the output is going to be the driven. So that's just real quick on basically finding out which ones are which. So in this system here, what is the number of teeth of our drivers? Anybody?
I can't tell what the teeth are.
So we got 56 here for this big gear. We got 16 here for this small gear, and the same on the other small gear.
So I guess 16.
So 16 for our driver, and our driven will be the 56. That is the gear ratio. However, there are 2 motors here. So if we were actually doing a speed calculation, then we would need to take that into account. So basically, we'd be saying speed in, which is the motors. Depending on what you're doing, there is it torque or is it speed, but basically speed in would be the combination of these 2 motors, assuming that they're running with each other and not against each other, because if you ran them against each other, this would break. So like, I don't know how well you guys can see this, but if these gears were moving down at their meet, these ones would have to be moving up, right? So basically this middle gear would have to be rotating counterclockwise. If the other motor was driving downward and these motors were equal, then this middle gear would not move, and you would burn out your motors and destroy them, which is never a good plan. But if you want a double motor system, that can give you more torque for the same speed, or more speed. You get the idea. The biggest idea with gearing is it's usually a trade-off. You're usually trading torque for speed, right? So if I had like a 30-to-1 gear ratio, where is it? Annotation. So a 30-to-1 gear ratio, right? What that would be saying is basically that's the division of the number of teeth. So this would be driven, or drivers. This would be driven. And what we'd end up doing is we'd say, okay, driver gear, right? If we go back to our initial thing, then we'd have our torque in, and we'd have our torque out, and then we'd have our speed out. Speed out, there we go, and our speed in. So basically what we'd be doing is asking how much speed do we have coming in. I'm just going to throw out a number, let's say 100 RPM, right? Actually, I'll make this easier. Say 60 RPM, right? So that would equal our speed out. Gosh, my legs. I'm wondering if it's going to be easier just to show you this in equation form, or if I should do it this way, but I think we're going to do it this way for now. Yeah.
Could you go back to the drivers and the DRS and the DRN? Why does a 30-to-1 ratio?
So it's not for this system. This one would be 16 to 56. This is just a random example. I just pulled 30 and 1 out of nowhere. It has nothing to do with this system, if that's what you're asking. I don't know if you said something there.
I did. That makes sense.
Okay. Equation form might be easier to kind of visualize this, honestly. And these slides are actually slides from an old class. Let's see if I can find his, yeah. Is this one? Yep. Okay. So that's the actual axle separation, which is that stuff that I was talking about that I don't really want to do yet, because it's nice to know if you're making gears, but it's not nice to know for really anything else. So I suppose like if you wanted to, you could do that. This will be a good one, I think, to do. This is a nice little setup here for an example. So, okay. Sprockets and gears work very similar. It's still number of teeth, and it's the same equations. Sprockets and gears, the only difference really is that sprockets like to be in certain numbers, and they allow you to do things from far away, right? You can put a chain in between them instead of having them right next to each other. But functionally, they work very similar. Another big difference is if you had two gears next to each other, right? They would have to rotate in opposite directions when they mesh. Sprockets don't. They rotate in the same direction because the chain is going around both, right? So those are really the only differences. The rest of the things are the same. So we'll look at this. We've got a 12 tooth and a 75 tooth, two sprockets. So, and we will say that I'll say the 12 tooth is the driven, or the driver. Which one of these gears, or which one of these sprockets is going to rotate faster?
The one with the 12 torque, the driven one.
So this one's faster, and which one's going to have more torque?
The one that's not driven.
So this one over here is going to have more torque. Yeah, I'll put more above it. All right. So if we look at it in the terms of like the gear equation, or the gear ratio equation, we'll say E equals, and then we'll say in drivers over in driven. So what is our what's the number of teeth for our driver?
Wheel.
12. And then our driven is 75, right? So let's say that equals what?
0.16.
Cool. All right. And then let's do speed. So let's say the speed of our driven is 100 RPM. Okay. So we can go ahead and say speed out divided by speed in is equal to E, which is equal to this over here, 0.16, right? So our speed in is 100 RPM. So we can put that at the bottom, and then in out is up here, and that equals 0.16, right? So basically what we can say is if we know the number of teeth on both gears, and we know the whatever speed is going into it, then we can find our speed out, right? So we'll just multiply by 100 because that's on the bottom, and we can determine that our speed out is going to equal 16 RPM, which, if you notice, is significantly slower than the smaller gear. So that fits with basically what we want. Then we could say torque out, or sorry, torque in over torque out equals the same thing, which is E, which is 0.16. So let's say our torque in, RIP Cynthia there. Let's say our torque in is 15, I'm going to make it simpler. Let's say 10 inch-pounds. So if our torque in is 10 inch-pounds,
Wait, I thought that our torque was 12 instead in D5.
no, okay. That is a good distinction to make. 1 second. Write torque out here. This number here is the teeth, okay? So this says 12 teeth, 75 teeth, okay? Torque, if I were to write it over here, I would symbolize by tau, which is this symbol, okay?
Yeah, I forgot. Letter.
Yes. I do get that the letters can get kind of confusing. I don't know why they chose a giant N for teeth number. That doesn't make any sense to me, but it's standard. So usually you just have to kind of take whatever's standard and go with it. Similarly, I don't know why a little n is speed, but whatever. So our torque in is 10 inch-pounds, and we know that our gear ratio here is 0.16. So what is our torque out?
62.5.
Okay. That's a bad place to write that. Do it over here. So 62.5 inch-pounds. And basically the way we do that is we multiply both sides by T out and then divide both sides by 0.16, which will give us this. So what this shows that we can do is if we know the number of teeth of our gears or our sprockets, then we can find not only our speed out and our torque out, but if we wanted to go in reverse, we could do the same thing. Or let's say we wanted, let's say we had 10 inch-pounds going in, right? This would be our T in. And then we wanted 100 inch-pounds going out. If we knew that, then we could find how many teeth we needed on a gear, right? Which in terms of FTC, that's probably what's going to be the most useful. Do you guys have this written down? Is it cool if I clear it?
Yeah.
Cool. So let's say you do calculations for something. What's something that you might, let's say you have an arm. I think I might want to put this on just like a paint or something, but let's say you have an arm, right? And it's got some sort of, I guess we'll do a claw again. Arm with a claw, and it is geared, okay? So you've got a gearing here, and this little gear is where your motor is, okay? So let's say you do the calculations based off of what we did last time. You remember statics, to find this has, let's say, 10 pounds, and this arm is 10 inches long, right? So you know that the torque over here is going to be 100 inch-pounds because it is the force times the distance, right? So this equals torque. All right. So if we wanted a motor that could hold this arm up, right, then our torque out needs to equal whatever our load is at the minimum, okay? Now let's say our motor can only supply 10. We'll keep it simple with simple numbers. Can only supply 10 inch-pounds, right, of torque. And that's going to be our torque in, because it's what the motor is giving, right? So if we have these, then we can find out just exactly what gearing we need to allow for this to happen, right? So basically what we do, and I'm going to go over here now, is we'd say T in divided by T out, sorry, tau out, equals our gear ratio, right? And we know our T in is 10, and we know our T out, which is 100. So we know our E, which is 0.1, right? Does that make sense to everyone? This little bit of math?
Wait, so you multiplied the length of the arm by the amount that the load holds.
Mm-hmm.
And okay, I see.
So from our last section, we talked about torque, right? And how torque is calculated. Torque is the perpendicular force times the distance. That equals torque, right? And torque is basically the rotational version of force, okay? And when we're talking about motors, everything's rotating, right? So we have to talk a little bit about rotational stuff. I'm not going to go too far into it because it does get confusing, but we need to at least know torque, okay? So yeah, we take our force, which is the weight at the end of the arm, which is 10 pounds. We multiply it by its perpendicular distance, which is 10 inches, because that's the length of the arm. And that tells us that this arm is going to be causing or creating 100 inch-pounds of torque, okay? So if we wanted to keep the arm up, we need to counteract it, right? Have an opposite amount of torque that is the same but opposite. So we need to produce 100 inch-pounds of torque in the opposite direction to hold it up. Does that make sense?
Yes.
Okay. So that's how we know what our torque out needs to be. And then your motor will have a specification. It'll say this is the maximum amount of torque that I can produce as a motor. And in this case, I just said that it was 10 inch-pounds. We'll look at some motors here in a bit, but we'll just say that for this particular motor, it's 10 inch-pounds of torque. And that's your torque in because it's what's being supplied by the motor. So basically we have the motor, which is the start of the system, and whatever you're trying to hold up, which is the end of the system, right? Which, if we have those, then we can decide our gearing, okay? So we know that our gear ratio is going to be 0.1, okay? Or our whatever you want to call it, gear ratio, speed ratio, etc. So if we know it's 0.1, then we can say that the number of gears, or the number of teeth, drivers, divided by the number of teeth of the driven needs to equal 0.1. Now that leaves some options. You could have 10 teeth to 100 teeth. You could have 1 teeth to 10 teeth. You could have all sorts of numbers, right? Typically, you will have certain gears that are available to you. I believe in FTC, you do have like 12 tooth and 75 tooth and maybe, I don't know, like 30 tooth, stuff like that. So you'll have certain options, right? And you'll have to decide which gears to use based off of what you need. So maybe you won't be able to get exactly 100 inch-pounds, but you might be able to get over 100 inch-pounds, right? So basically, if you had any number less than 10 and any number greater than 100, that combo would work for the torque that you need. It would just be slower. So let's say you had, what is a standard number? I think 128 is a standard number. So let's say you had a 128 tooth gear and you had a 12-tooth gear, right? 12 divided by 128 is 0.09, 0.09, which is just barely not enough. So maybe you have to take it down a little bit. Maybe you go to a 6-tooth and a 128 tooth, right? And that should give you something that's above 0.1. So basically, what you're looking at here is which gears can I use to be able to get the output that I need, right? And that's most of engineering, honestly. It's saying, here's what I have, here's what I need, what's the best fit, right? And that's really what's going to happen with your powertrains and your gear transmissions. Are there questions on any of that?
For the 6/128, that's actually less than 0.09.
Oh, sorry, you're right. It's 0.04. Yeah, so I said that wrong. 0.09 would just work, just barely work. If you had a 12 and a 75, it would not. So it's lower number. So this would work for the torque output, and 0.046 is the 6 divided. So that would work for the torque output. This is what you need. And then let's do 12 divided by 75. Yeah, 0.16. That would not work for your torque output. So, sorry, I said it backwards a second ago. Smaller number is better for torque. Bigger number is better for speed. Okay. So speed and torque. And that's why it's usually called the speed ratio, is because larger means more speed. So yeah. Sorry for that, and thank you for catching me. Is there any questions on that bit? No one?
No.
Cool. All right. So, and I think I'm going to end class early today, but I do want to show you what this is going to be for. So the gear stuff is some of the simpler stuff, and we might do some more gear things next class, but we're going to be looking at more interesting gears. Specifically, worm gears are very interesting. Belts are nice. Sprockets and chain. I'll just say chain. These are all different things that are all different types of power transmissions. They're all very similar to spur gears, which are the gears that you're used to, but worked very slightly different for each of them. And you can actually see worm gears here, a little bit about them. Basically, they don't back drive. That's nice. They're compact because they're small. This is a worm gear, by the way. And instead of number of teeth for the drivers divided by number of teeth for the driven, worm gears, the way they work is it's number of leads on the worm versus number of teeth on the whatever you're driving. So this is a typo. That should say spur gear. So basically, we'll talk about worm gears more next time because they are interesting and useful if you don't want a back drivable system. But specifically, I would like to show you a chart, and it's because that's what we're going to be using for deciding motors, and it is this type of chart. Can everyone read this a little bit?
Yes.
Okay, so this is a performance map for a motor, okay? All motors have these when they are put out, okay? So your motors, the ones that you guys use for FTC, the little Andy Mark motors, they have these as well. You can go on their website and find it. This one is for a sim motor, which you guys aren't going to use sims. Sims are larger motors. They're usually used for FRC. But this is a good representation of what one of these charts looks like, okay? So basically, we have some trade-offs here, and that's what's at the top. You have the current that you're running the motor at, you have the power that it's outputting, you have the torque, then there's two versions of torque actually, and they're just in different units, and then you have the speed. And then efficiency and heat we'll look at later on, but not quite yet. But the big important thing for this class, like this session, is the trade-off between speed and torque, okay? So if you can see, as the torque gets larger, the speed gets smaller, right? So that's showing basically if you run a motor faster, it's not going to be able to push as much, okay? And that's going to be really important when we're starting to look at what motors to use. Another important thing is the current, because we're going to say, I forget what current usually the FTC motors are run out, but I'm going to assume it's probably like 30 amps. I can ask somebody who is a programmer, but we're going to assume it's 30 amps for now. So what we'd be saying is on this performance map right here, we're going to look at the current and say, okay, we want to limit our motor to run at 30 amps. Now 30 amps is going to be around here. Can you guys see that? Are you guys able to see the marking there?
Yeah.
Cool. So it's going to be somewhere in between there. So we know if we run it at 30 amps, it's going to have somewhere around 5 inch-pounds of torque, because that's the between here, and it will be somewhere around 4,000 RPM, okay? And we're going to start looking at this sort of stuff next class, because this is going to be what's important when we're choosing a motor. So maybe we have one motor, an Andy Mark, let's say, and at 30 amps, it can produce, let's say, 2 inch-pounds of torque, okay? And then we have a sim, which also at 30 amps, it can produce 5 inch-pounds of torque, okay? So let's say we're trying to make something that can climb easily. We might want to go with the sim, but the problem is the sim is heavier and the Andy Mark is lighter. So maybe the trade-off for weight isn't worth it. And maybe we can get the same effect with some clever gearing, right? So maybe we will actually want to use the Andy Mark with a 3-to-1 ratio instead of just the sim by itself. And that's going to be what this next session is, section of this class is mostly going to be about. It's going to be about what motor and what gearing do I want to use for the application, okay? So that's kind of where we're going with this. And I'm going to call class early because I have a lot of work to do today. But are there questions on sort of this little... This has been sort of a loose intro into what we're going to be doing. Does this all make sense?
Pretty much.
Maxim, Cynthia, do you guys have some questions?
No, I think I'm good.
Cynthia, what about you?
No, not really.
Okay. If you do have questions, feel free to ask. You can also ask on the Discord in the mech Q&A, so that you guys can just take a sneak peek at what we will actually be doing next time. I would like to show you one chart. Here we go. I'm gonna have to reshare this, I think, because it's on a different window. Yes. All right. So here is a problem that we're actually going to do next time. Basically, it's if we have this size robot and we need to climb this amount in this time, what kind of system are we going to need? So if we go with a winch, so like a cable, what's the drum going to look like? Which motor are we going to use? We'll look at some of the performance mapping, and then we'll actually figure out the problem. And then we're going to go from there and talk about efficiency and ways to apply that to FTC. This one's going to try to be more FTC focused. The last one, statics, is useful for all sorts of things, so I wanted to just cover statics. This one, you won't need it other than choosing motors and that for FTC, or choosing applications or choosing gearing. So I want to make sure it's specified to what you guys have. And I actually might run over to the office where we meet for FTC and grab the items that you have available to you and specifically go over those items because I think that'll be what's most useful. That sound good to everyone?
Oh yeah.
Cool. Everyone planning on making it to next week's class?
Oh yeah.
Maxim, Cynthia?
Yeah.
I'm going to try.
Cool.
Because I've got a lot of stuff going on right now
Do or
with
do.
school and setting up for everything for next year.
Okay.
So
Just checking because I do want to make sure that we have some attendance. I will try at this Thursday meeting to push more people to come as well. Mainly, I want to keep doing this class, but the problem is like I do have my own work to do, and if we don't have very many people coming, then it becomes questionable as to whether or not I should be doing this class right now. I think 3 or more is a good number, like a number that is a good enough trade-off for me. So try to get your friends to come, it doesn't matter where they are or where they're from or what team they're in. If they're in FLL or FRC or any of those, or even from a different school, still try to get them to come to the class. I'm willing to have anyone here. So
Even if they're not in robotics.
sure, yeah.
My friends would never do this.
Yeah, I don't care who they are, as long as they will or want to learn this sort of thing. Have them pop in, at least check out a class. This is just for you guys and whoever wants to. So the more people, the better. Yeah, spread it like wildfire. Other than that, I think I'm going to call that class for today.
Cool. Bye. Wait, is there any homework?
There is not homework for this class. I would urge you in your free time just to go check out maybe a video or two just on gear ratios. It's not a hard concept, so I'm not going to assign homework on it because I think that homework would be very tedious. But just to make sure that you sort of review the information, look up like any video on just gear ratios and how they work. That'll, I think, drive it home pretty easily. Because that gear ratios is the one thing we're going to 100% need to know for this section. Okay, it's an easy thing to know. Just it's going to be required. So, sound good?
Cool.
Awesome.
Bye.
Cool. I will see you guys next week.